Okay, good. So good morning, good afternoon, everybody. And thank you for joining this new talk of the Intelligent Bioinspired Mechanical series. And today we are happy to host Dr. Jianxun Wang, which is an assistant professor of aerospace and mechanical engineering at the University of Notre Dame since 2018. He received his doctorate in aerospace engineering from Virginia Tech and was a postdoctoral researcher at the University of California, Berkeley. His research focuses on developing data-driven methods, including physics-informed machine learning, uncertainty quantification, and Bayesian data simulation, to mention a few. His research also involve modeling of cardiovascular flows and inverse problems in CFD applications, as well as turbulence modeling. And today, Dr. Wang's talk will be focused on physics-informed deep learning with the objective to enable effective learning physics knowledge. I remind everyone that this talk is currently recorded. Is being recorded. So if you are not willing to show yourself, just turn off your webcam, and question time will be at the end of the talk. So you can simply write the question in the chat or raise your hand and turn on your microphone to put your question. So that's it. And Dr. Wang, the floor is yours.
Okay, thanks. Thanks for the kind introduction, and thanks again for inviting me. I'm very glad to give a talk at this IBiM seminar series. Well, today I'm going to introduce my previous and current research that are related to physics-informed deep learning, but I'm going to focus on the fluid mechanics and the fluid dynamics applications. But in general, the techniques I present today can be applied to any other computational mechanics problem where the governing PDEs are given or partially given. So first, I'd like to acknowledge my PhD student, Han, Luni, and Pan. Most of the work I present were conducted by them, so to give them credit. So first, let me introduce the background and the motivation. So we know the physical phenomena are usually modeled by partial differential equations. And in most cases, we need to use the numerical approach like the finite difference, finite volume, or finite element method to solve the equation and enable predictions. However, this traditional numerical techniques often require significant computation efforts, particularly for a complex system with multi-scale and multi-physics features. For example, to construct this 3D cardiovascular models and to perform the hemodynamic simulation is a time-consuming process, which typically include the segmentation of the model from the medical images and to generate the mesh, numerical solving the discretized system and post-processing the result. If we also need to consider the interaction between the fluid and the structure of the vessel walls, the computational cost is going to be dramatically increased. However, towards the clinical use, the ultimate goal is to enable the real-time predictions. And also, like in many cases, we need to consider the uncertainties from the boundary conditions, the geometries, because the geometry is second from the medical images, and like the material properties. So this related to the uncertainty propagation and quantification. And when we use the model to support the surgical planning, we need to perform the optimizations. So in all these scenarios, we have to run the forward simulation for many times, thousands of times. So this first principal model we use traditional numerical methods are prohibitively expensive for either real-time or this so-called man query applications. So therefore, we need to make this simulation super fast. One typical option is to develop a surrogate models. Traditional surrogate like Gaussian process have the difficulties to deal with high-dimensional problems with strong nonlinearities, and usually the quantity of interest only limited number of scalars. If you want to do the field surrogate to directly provide the field predictions, is very hard. Recently, the neural network-based deep learning techniques has been demonstrated as a promising alternative because of its universal approximation capability and strong nonlinearities. So we have built a conceptual neural network surrogate is in a straightforward way. Here, I use a very generic network type and architectures. It's no matter fully connected convolution or graph neural network. So it takes the input, like the parameters we care, the inflow, outflow boundary conditions, geometries, mechanical properties, and other operational parameters. And hopefully it can directly predict the corresponding flow solutions, such as flow, velocity, Walsh stress field, and so on. To achieve this, we need to train this neural network, right? Which is traditionally based on a large number of label data. It's more like a regression. So it is known that this training data pairs or label data pairs are obtained either from the high fidelity numerical simulations or experiment, and both of which are very expensive to obtain. And we know in many practical scenarios, we only have a very limited number of label data. So if we only rely on data, it implies that we treat this system as a black box. So this mapping is definitely not a purely black box to us. Instead, in many cases, we know the governing equations, or we partially know the governing equations, or we the underlying physical constraints or physiological principles. So meaning that the neural network output should satisfy those physical principles and constraints. So if we can utilize this no physics, like governing equations or constraints to inform or to drive the neural network training, so we don't need too much, we don't need to rely too much on the label data, or either we don't need the data at all, which is to directly use the neural network to solve the parametric governing equations. So this is a core idea of physics-informed neural network. You might heard the PIN. In general, the different information such as equations, boundaries, and data can be unified in the multi-object loss function and learned by the neural network. Actually, using the neural network to solve the differential equations is not new, has been explored decades ago in late 90s, but haven't had a big impact back to that time. Most recently, this idea has been revived due to recent advances in machine learning and deep learning. Kanyada and his co-workers have developed the seminal work of the physics-informed neural network using the modern deep learning techniques, where the PDE residual is incorporated into the loss function of a fully connected neural network as a regularizer, enabling training in a small data regime. And our group has also been working on the similar directions of physics-informed learning since 2017. And you can see in the past 2 years, the PIN has been widely applied to many scientific problems. But here, I don't have time to give you a throughout review on this. Well, the PIN is kind of successful and hard, but it's also good to know when it fails and what would be the challenge. So in current PIN formulation, one of the biggest challenge is this multi-objective non-convex optimization. This multiple objective loss component have posed great difficulties on the neural network optimization. Here I will give you an example. It is known that the requirement of the data can be completely avoided if the initial and boundary conditions are properly enforced. Namely, we're using the neural network to solve the PDE deterministically without any label data. So in this case, the boundary condition becomes critical, right? So in the PIN, the boundary is formulated as part of the loss function, and which can be seen as a soft constraint. But the problem is it's hard to determine the weight parameters of like the lambda for each component. And we have observed that there is a competing effect between the equation loss and boundary loss. For example, if we specify a small penalty coefficient for the boundary C, the lambda is 1, we find that equation loss can be driven to 10 to the minus 4. However, the boundary loss remains to 10 to the minus 3. And if you check the learned or the solved solution, it is not physical, and which is pretty long compared to the CFD benchmark. On the other hand, if we focus on the boundary with a large weight, and now the boundary loss can be reduced to 10 to the minus 7, while the equation loss trapped in a bad local minimum. So the corresponding solution is totally wrong as well. Actually, if you evaluate a wide range of the weight, just from 1 to 1,000, none of them could give you reasonably the reasonable physical solutions to the Navier-Stokes equations if no data are provided. Therefore, we choose to encode this boundary in a different manner, in a hard manner, by introducing a specific solution function, distance function. And if we can impose the boundary in this in a strict way, like hard impose the boundaries, the optimization becomes much easier, and the physical solutions can be learned compared to the CFD. So we first developed this more like this physics-informed neural network for surrogate modeling of fluids. So the input layer take the spatial temporal coordinate and also the variable parameter theta, including the parameterized boundary conditions, geometries, mechanical properties, and it outputs the solution variables like the velocity and pressure. Instead of imposing the boundary condition as a panel charts, here we modify the output layers by encoding the boundary in a hard manner. Namely, the initial and boundary condition will be automatically satisfied by construction. So the training will be constrained or even driven by the law of the conservation laws of the Navier-Stokes, conservation laws of the fluids, which is the Navier-Stokes equations. So this physics-based learning can be formulated in a deterministic way, as I mentioned in the previous slides. That is, we can simply define a loss function to minimize the residual of the Navier-Stokes equations. However, when we want to use a neural network, we definitely want to leverage data, even the data are sparse. But if we want to assimilate data are usually noisy and has measurement uncertainties. And also like this physical models are not perfect. Those could have the modeling inadequacies. So in order to consider this uncertainty and make robust predictions, a Bayesian formulation is preferred. So here we developed the physics-informed likelihood function instead of loss function, and we're trying to optimize the posterior of the natural parameters by approximating the posterior using non-parametric variational inference approach. Particularly here, we minimize style discrepancy, which is kind of equivalent to minimize the KL divergence or maximize elbow in a non-parametric way, if you are familiar with variational inference. So here I'm showing you some results of the data-free deep neural network surrogate. Let's consider a blood flow in this idealized stenosis. So here our goal is to build a surrogate, which is very simple. Take the different stenosis geometry as input, and then we hope to rapidly predict the corresponding flow solutions, like the velocity and pressure in a second. So in this case, we didn't use any data to train the neural network. Just try to test the backbone power of the physics inform the Bayesian learning. So this is more likely to use the neural network to solve the parametric Navier-Stokes equations with given boundary conditions. So The prediction results are pretty good. I'm showing you the neural network predictions for 3 randomly picked different stenosis geometries. And the CFD here is only for comparison. We didn't use them for training. So we can see for both the velocity component, the contour of all different stenosis geometries agree with the CFD benchmark very well. And also the nonlinear pressure drop can be accurately captured. Here's another idealized vector flow, the aneurysm flow. So similarly, we can build a fast surrogate that take the geometry of the aneurysm as input and directly predict the corresponding flow patterns. Again, without any trained data, the neural network is able to learn the flow solutions and predict the flow field accurately. Here I'm showing you the prediction result for 3 different aneurysm geometry, from mild one to at the left and to the bigger size aneurysm on the right. So you can see the network prediction agree with the CFD very well. And for the aneurysm, we care about the washout stress because clinically it is related to the onset, progress, or even rupture of the aneurysm. So the network can accurately capture the washout stress distributions along the vessel wall. All right, so with such a very simple neural network-based surrogate or simulator, we can do a lot of things that involves a large number of model evaluations. For example, we can easily propagate tons of Monte Carlo samples in a second to quantify the uncertainty in the vessel geometry and the blood property like the viscosity. In the previous slides, I didn't use any data and just try to test the backbone power, but usually we want to involve some data. If we have some sparse data, for example, we have the velocity measurement on these sparse locations measured by a limited number of sensors. So since the data are too sparse, we cannot learn a physical solutions only based on this data using the data-driven learning. But if this process is constrained by the divergence-free condition, the learned solution becomes much better, but it's still not quite correct. Once the learning is constrained by both the conservation of mass and the momentum, the learned solution is almost identical to the reference, to the CFD reference. But here, you might be wondering that I already demonstrated the flow can be learned even without any data, particularly for this flow. So how does the sparse data would help? The short answer is the data will help to facilitate the convergence, since more information is introduced and is simulated. So the 2 figures show the learning curves for the velocity and the pressure. The blue one is data-free physics, physics-informed learning, while the red one is the physics-informed learning plus the sparse data. It is clear that with same number of epochs, the arrow, the training epochs, arrow is more than order of magnitude lower when the data are incorporated. But like I said, the data is not only sparse, and in many cases, it is also like excuse me, so I'm not sure if I'm showing the right screen. So are you seeing my right screen?
Yeah.
Okay, because I cannot see which screen
you mean the pointer?
I'm showing.
You mean the pointer?
Yeah, pointer and the screen, because I have 4 screen. I'm not sure if I'm showing it. Yeah, okay. I just want to make sure. Okay, cool. Thank you. So let's continue. So like the purely like I said, the data is not only sparse, but in many cases they're also noisy. So the purely data-driven learning fails by only using the sparse and noisy data. In contrast, the PDE driven learning can accurately reconstruct the flow, but also provide the predictive uncertainty since our framework is formulated in the Bayesian fashion. So let's check if the estimated uncertainty makes sense by changing the data noise. So if we use noise-free data, the prediction uncertainty is very low in most regions. And if the data noise increases to 10%, the uncertainty of the prediction also significantly increased. If we further increase the data noise to 20%, the standard deviation of the prediction also doubled. If you check the mean prediction, they are similar for all three cases, and they all agree with the CFD reference well, showing the robustness of the variational Bayesian formulation. We also can reconstruct the flow field from a sparse and incomplete measurement. For example, if we sparsely observe the flow velocity and try to infer the pressure distribution, here we consider another idealized vascular aneurysm bifurcation. Now the flow inlet is at the bottom and the blood goes up to the two bifurcation arms. The aneurysm on the top. So this time we only take a sparse velocity measurement on this 6 slices and try to reconstruct the entire velocity field and also infer the pressure distributions. As expected, this measurement are definitely too sparse to reconstruct the flow purely based on data. And we cannot obtain any pressure distribution since we have no pressure measurement at all. So with our physics, Bayesian physics informed learning, we not only can reconstruct the velocity field accurately, but we also can infer the pressure distribution reasonably well. And this is like a 3D case for the idealized aneurysm, where we're trying to uncover the near wall blood flow using only very sparse internal flow measurement. And here you can see the near wall velocity and the wall shear stress can be accurately inferred. And this is very useful for the cardiovascular measurement and imaging. So this is more like the PIN formulation. So PIN uses the continuous learning formulation based on the pointwise fully connected neural network. So we can directly leverage the auto differentiation to compute the derivatives in the PDE-based loss function. So it won't have a discretization error. So this nice feature enables us to accurately capture the discontinuity. But I mean, despite the great promise, the current PIN formulation, the fully connected PIN master suffers from the scalability issues when it comes to learning the operators in a high dimensional input space. The training costs will significantly increase for the complex problem, especially with parametric variations, since the PDE residuals has to be evaluated on a massive amount of collocation points in high dimensional input space. And you can see this is a scalable test of the PIN by NVIDIA. Even with massive GPU parallelization, it still requires hundreds, thousands, or even millions of epochs to reach a convergence. So to enable efficient learning for problems with a large spatial temporal solution field in the high dimensional parameter space or input space, the convolution neural network structures, aka the CN structure, has attracted increasing attention in the scientific machine learning community. Compared to the fully connected net, the CN usually needs order of magnitude fewer parameters, and it does well positioned for large-scale, high-dimensional surrogate modeling problems. So in a similar vein, the physics-informed CN can be developed as follows. The goal is to learn the solution of the PD in a parametric setting. So the F is a PD operator defined in the physical domain, omega P, and parameterized by mu. And B is functional for the boundary conditions. So in contrast to the pointwise fully connected formulation here, the entire discretized solution field can be approximated by CN. So it will enable the image-based end-to-end learning, and it can directly generate the solution over the entire field, entire domain, instead of point-wise output. Moreover, the trainable parameters are defined by a bank of filters, which are shared over the entire domain. So they often have much less training costs and better predictive accuracy. So similar to the pane, the training can be formulated as a constraint optimization using the governing PDEs and the corresponding boundary conditions. All the spatial derivatives are numerically approximated by numerical discretization, like the finite difference. And the constraint of the boundary condition can be either treated as Pavlov terms, like pane, or strictly encoded into the network structures very easily. We choose the latter. So here is an example of the network structure we use to learn the solution of parametric and average Stokes equations. And you can see the network architecture is built with input channels composed with physical parameters and the coordinate of the geometry. And the solution field, the solution field of each state variable, like the velocity component and pressure, is represented by a separate sub-CNN net. Therefore, the trainable parameters are decoupled for different solution variables, and each subnet has an identical structure, and all the subnets are trained simultaneously with a unified physics-based loss function constructed by the PDE residuals. And here's a demo result for the fluid flow passing a square duct with a complex inflow boundary condition. You can see the CNN can accurately predict the flow patterns and like this isolation regions. They all agree with the CFD benchmark pretty well. But the classic CNN has problem because classic CNN had originally been developed for the image recognition and processing. So the convolution filters are designed for images or image-like data. That is why you find all the existing works on the PDE-informed CNN, they'll only be able to deal with problems defined on the rectangular domains with uniform meshes. They usually cannot go beyond rectangular image-like domain because of the intrinsic limitation of the CNN, the convolution in the classic CNNs. However, in many practical applications, the geometries is way complex than the rectangular, which need non-uniform meshes all the time, like patient-specific geometries or the flow past complex automobiles and so on. So how can we still leverage CNN for this problem with irregular geometries and non-uniform meshes? First, I would like to show you why the irregular geometry is a big issue for CNN-based discrete learning. So we know even for this simple irregular geometries, the boundary fitted mesh in the figure A, the classic CNN are not directly applicable, like I said, since the unstructured mesh data is non-Euclidean. So the shape invariants that justify the use of the classic convolution operation is no longer valid. So to enable the use of a classic CNN backbone, usually the so-called rasterization is often performed to pre-process the data in the data-driven learning scenarios. It converts irregular shape into the uniform meshes, and the geometry is usually either represented by this binary or the sign distance function as shown in the figure B. However, this approach fails to operate in the physics-informed learning due to a few reasons. First, the rasterization. After rasterization, you can see the boundary becomes stepped and zigzag, which will introduce a lot of aliasing errors under the low or moderate image resolution. And second, using the binary or sign distance function representation, it's difficult or even impossible to impose the the PDE boundary conditions, and thus the physics-informed learning will fail, and particularly when the label data are scarce or even absent. Although, of course, a sufficiently high resolution can reduce the representation error and elevate some of the alpha meshing issues to a certain extent, but it will significantly increase the training costs and definitely cause the memory issues. And lastly, the conventional rasterization or voxelization for 3D case, they are not differentiable with respect to the input decide space. So it's going to limit its use for geometry optimization for the decide purpose. So to push forward the discrete physics-informed neural network for complex problems with irregular domains, we propose two strategies. So the first strategy is to utilize coordinate transformation techniques to map the solution field from a irregular physical domain to the rectangular reference domain. We have developed this so-called FAGIO-net, where the key idea is pretty simple. We encode the elliptic coordinate transformation into the CNN architecture, where the PDE is actually imposed on the transformed rectangular reference domain. So the elliptic coordinate transformation is a deterministic one-to-one mapping, and which can be pre-computed. So there's no overhead for training the neural network. Now we can use the backbone power of the classic CNN even on the irregular domain. And this work has been published on the recent Journal of Computational Physics. And our second strategy is to leverage the geometric deep learning to directly, where a more general convolution operation is basically directly defined on the non-Euclidean space. We know from the convolution theorem, the convolution can be defined on the non-Euclidean structured data, like the mesh or graph. So by approximating or by solving the eigendecomposition of the graph Laplacian. So to construct the physics laws, the Galerkin method is used to discretize the wake for PDE residuals. So we call this as a neural Galerkin graph convolution network. So let me first briefly introduce our first strategy, that this so-called physics-informed geometry adaptive CNN approach, the FAGIO-net, which is try to enable the direct use of the classic convolution on the for the physics informed learning for irregular geometries with non-uniform meshes. Like I said, the key idea is to utilize the coordinate transformation techniques to map the solution field from the irregular physical domain to the rectangular reference domain. For example, the left side is a physical domain with the coordinate x, and the right side is a rectangular reference domain with the coordinate c. If we can define this one-to-one mapping between two coordinates, meaning we know the forward map, either we know the forward map from the reference to the physical domain, or the inverse map from the physical domain to the reference domain. So we should be able to reformulate the PDE on the reference domain, and the PDE loss function can be defined on the reference domain instead of irregular physical domain. Therefore, the classic convolution are valid. In most cases, the analytical form of the forward or inverse map is not available for any arbitrary geometries. But we can approximate the numerically by solving a boundary value problem by solving elliptic equations, because we can define this boundary value problems and to find this one-to-one mapping numerically. For example, we can solve Laplace equations on the physical domain. I will skip the math because I don't think I have time to finish all. But like I said, we can solve the elliptic equations and to find out this deterministic one-to-one mapping. And this can be pre-computed, so it won't introduce any overhead for training the neural network. Okay. These are a little bit detailed. So basically, we will compute the Jacobian of this coordinate mapping, and we use this Jacobian and to convert the derivatives in the irregular physical domain to the regular reference domain. And by using all these operators, which is pre-computed, and we can modify our loss function and a CN physics-based CN convolution filters, and so that now the PD informed optimization is reformulated on the reference domain, and so that we can perform the physics constrained learning using the classic CN formulation. So the idea is pretty simple. So this is an overview of the PDE-Net. It takes the control parameters like the boundary parameters, geometries, and others, and define on the physical domains as an input channel, and it will output the solutions on the reference domain. Okay. Again, the boundary conditions for both directly or movement boundary conditions are strictly imposed here as using the finite difference padding. So we don't have any boundary constraints in the loss function. So the loss function is only defined by the PDE residuals on the reference domain. So now we can learn the solution of a parametric PDE even without using any data. So let me show you some numerical results, which are quite encouraging. So here is we use the PDE-Net to solve the heat equation on the irregular domains with this bad shape. It agrees with the finite difference benchmark very well. And the second case demonstrate our PDE-Net can accurately learn the solution of the Navier-Stokes, steady Navier-Stokes equation on the patient-specific vector geometries. So both the velocity and the pressure field can be captured well if you compare with the CFD reference. So this is the first time to use the CN to solve the PD on irregular domains without data. And this can be, of course, to extend to parametric setting because we want to utilize this as the surrogate. Right, so here I'm showing you the geometry with a little bit different topology. This is like a donut, and this time the inner circle boundary condition is parameterized as input, and you can see for different boundary conditions, the learned solution agree with the finite volume benchmark well. And this is the result for the parametric Navier-Stokes equation. So this time. The geometry is varying, and you can see the geometry is actually input this time, and by varying the geometries from the divergent convergent channel and to the convergent divergent channels. So all the solutions, including the velocity and the pressures, and can be rapidly predicted without any data, and they agree with CFD reference pretty well. And this is go to a high dimensional case. So this time the PDE-Net learned the solution field of the Poisson equations with a stochastic source term. So this time the input is the stochastic source term for the Poisson equations. And we use a Gaussian random field to represent this source term field. Which is expressed by the Cahunen-Love expansion truncated with 20 KL modes. So the intrinsic dimension of this problem is 20, meaning that the input space has a 20 dimension. We have a 20 dimensional input space. So even in such a 20 dimensional input space, we randomly generate the input and to predict the solution field of the Poisson equation. And you can see they agree with a reference reasonably well. This is a high dimensional case, and we can do the high dimensional UQ. So let's compare our PDE-Net with a PIN, with a fully connected PIN. So if we fix the training budget, meaning we train both network for the same amount of time, approximately the same number of iterations, about 1,000 iterations. So it's clear that the visual net already, you can see the capture it already learned the solution for both velocity and pressure compared to the CFD reference. In contrast, the fully connected pin only learn a trend for the velocity with a large arrow, and it basically failed to capture the pressure at all. And if we fully train the BOSNet with sufficient number of iterations, and you can see our PhaGeoNet only needs 1,000 iterations to converge, but the fully connected pin needs 10,000 iterations. Even so, the accuracy is still much lower than the CN and still fail to learn the pressure distributions. So demonstrate our approach are 10 times faster and more accurate. Yeah, I still have some time. I want to show you I will show you the first strategy, but let me briefly show you some preliminary results for our second strategy, the neural graph convolution network. As you can see, we developed this graph convolution network where the input directly take the unstructured geometry, unstructured meshed geometry and the parameters. And the waveform PDE are constructed by the Galerkin method based on the polynomial basis. And this time, the nodal feature of the output graph directly define the solution coefficient for the Galerkin reconstruction. So the optimization is still solved by the stochastic gradient descent. So to demonstrate the effectiveness, here I'm going to show you a few examples. So the first, the backbone capability of the Galerkin GCN for solving the wall post PDEs, like the forward problem, is tested on both solid and fluid mechanics problems. Again, no label data were used to test the backbone power. So in particularly this structure deformation of the 2D elastic plate is learned purely based on the linear elasticity equations. And you can see the Galerkin GCN predicted the displacement field matched very well with the reference result by the finite element method. And similarly, the Galerkin GCN is trained on the Navier-Stokes, and now it captured the internal flow field of this 2D vector tube. And the prediction results are accurate compared to the CFD reference. But we are more interested in the inverse problem. Here I'm showing you two results to demonstrate the potential of the Galerkin GCN for solving the inverse problem with sparse labeled data. So this time, still the same 2D elastic plate deformation, but this time we don't know the material property, like the lambda and mu, the material property are not given. But instead, we have very sparse observations, like the deformation on this 5 points. And you can see the network not only can predict the entire displacement field, but also can accurately infer the two material properties after 2,000 iterations. So here the dashed line is a true parameter values. So similarly for this 2D standardized stenotic flows, but this time we don't know the inlet velocity profile. So within the proposed learning framework, by assimilates very sparse measurement data, we not only can accurately capture the internal flow solutions, but we also can infer the velocity profiles accurately simultaneously. So this is like a field inversion. And I'm just trying to show you this forward and inverse problem can be solved in this unified manners. Okay, so this is like we can use a similar idea to enable the super resolution of the flow data without a high resolution label. And this is very useful in many scenarios. For example, I'm interested in the cardiovascular flow. So the 4D flow MRI data often has low resolution and pretty noisy. And to enhance the resolution and super resolve, the flow imaging is significant, but we really cannot have the high resolution MRI data for training. So using the physics-informed super resolution net, we can enable this high resolution label free training. This time the input could be the low resolution flow field, and the output is super resolved flow solutions. And to formulate the loss function, we can use the Navier-Stokes, we can use the boundary conditions, and we also can leverage the low resolution data. And I don't want to go into too much detail. I just used last few minutes to show you the results. So the left is a low resolution MRI field with MRI flow field with noise. The upper one is corrupted with Gaussian noise, and the lower one are corrupted with MRI type of noise, which is non-Gaussian. If you directly do the bicubic interpolations and to super resolve the flow, which is the typical way you super resolve the flow field, it's pretty bad, of course, but use our physics informed network to super resolve the solutions. It can eliminate large Gaussian or MRI noise and agree with the ground truth pretty well. And this definitely can be used for the if the boundary condition is not given. And so this time, for example, the inlet is not given, but instead you can do several slices of 2D PCMI. And by utilizing the 2D PCMI, this kind of like the sparse data, we can do the super resolution in the forward manner, and also we can infer the inlet velocity profile pretty well. And we can extend it to the high dimensional case, meaning this time the scientists can opt to only run their simulation or experiment only at the low resolution. And then we can upscale the result back to the high resolution, to the target resolution. So this will save cost and speed up the scientific investigation discovery. And even for this parametric super resolution, and we can enable the parametric inference, meaning in all of this case, we don't know the inlet boundary condition, and the inlet is like a random field. We don't know, but if you only provide me the low resolution, I can accurately infer the inlet velocity profiles in this parametric way. Okay, so this is very useful and interesting. I'm not sure if you can see here we have two curves. One is inferred, one is a ground truth. They are almost like overlapped. So meaning the inferred results are pretty accurate. And lastly, I'm showing you the preliminary result for super resolved spatial temporal reaction diffusion data. And this is like large scale dynamic system. And I'm trying to show you that this method can also be scalable to the large scale data. This is low, and this is our super resolved result, and this is reference. So let me quickly show you some ongoing work in our group. So one of the challenge for the real life application of the techniques I mentioned is how do you parametrize or represent the geometry space for the real patient space specific cases. So the representation or perturbation of the complex 3D vector geometries for the patient specific case are definitely non-trivial. So to tackle this challenge, we developed the state-of-art geometric representation and the mesh morphing techniques. So we can morph from the one patient to another patient, and we can do the correspondence. And based on that, we can leverage the unsupervised geometric learning approach to encode this real 3D vector geometry to the latent space. And then we can map it back to reconstruct original geometry through the decoding process. So we can randomly generate synthetic physics specific geometries in the latent space and to enlarge our input geometric sample space very easily. And this is like the real life predictions for the real patient specific geometries for the aorta. And this is the wall shear stress predictions. And another lie is to handle the dynamic case, even with mesh deformation. So we need like to design more advanced graph embedding and the attention-based transformer to handle the long-term dynamics. For example, this is a prediction result, the machine learning prediction result for this flow passenger at Reynolds number equals 700, and this is CFD. And you can see even for this long-term dynamics, and we can accurately capture it and without like a lot of error accumulation. So it agrees with the CFD very well from the transition to the vortex shedding. Okay, and we also want, this is like we directly handle the unstructured mesh. So this is like the graph deep learning. And this is the dynamic mesh deformation. This is a hypersonic flow, and you can see the mesh is actually moving, and we directly handle the deformed mesh use graph convolution and transformer. All right, so I think this is basically what I want to share with you guys. And here is the list of our recent publication on this topic, including the surrogate modeling of the Navier-Stokes Bayesian physics informed network and the CM formulation for irregular geometries and the superresolution. So if you are interested, please download from my website. The manuscript are all available. And also my GitHub, most of the code are available if you are interested, you can play with. Okay, so thank you for your attention, and I'm happy to take any questions.
Thank you very much, Dr. Wang, for this very brilliant surveil application of physics-informed machine learning. So I think there will be questions for you. So if anyone want to ask question, can write in the chat or raise the hand and simply speak. There's one question in the chat saying that, could you please speak to how the 5GeoNet of similar CNN based applications can be extended for multi-phase flows? So
yeah, I think I think it can be extended to multi-phase flow easily. So if I go back to so like here, if we have multiple like the physical state variables, and we can basically add more subnet, and what we need to handle is to handle the interaction between the different phase. So as long as you have the governing equations, and I think you can basically use the similar approach and to do the similar things. So it doesn't matter it's a multi-phase flow or a single phase flow. Actually, we are using this to perform the FSI, the fluid structure interaction. So we have the structure net and a fluid net. So the basically the fluid structure interaction can be solved like in a few different manners. So we don't need to do this loose coupled iterations like what we did in the numerical FSI. So here you can, if you know the governing equations, this would not be a big problem.
Okay. This is another.
Okay.
Yeah.
Okay.
Can you read the question from the chat, or should I read that for you?
Yeah. I'm trying to open the chat.
Okay. I can read for you if you prefer. There are some questions.
Okay. Yeah.
There is a question saying that if you could explain if I get two more PIDs in the model, like advection diffusion problems, we just put both PDEs and corresponding boundary conditions in one cost function. This is the next question.
So if I get two more PDEs in the model, we just put both PD and so like Navier-Stokes equation, you have three PDEs, right? So the PDEs will go to the loss function to inform the learning process. But for the boundary condition, of course, you can put it into the loss function. But at the beginning, I said this may complicate the optimization because you have the multiple components and sometimes they have competing effects. So what I suggest is for the boundary condition, we actually have a way to encode it into the network structure. So by construction, the boundary condition already being satisfied. You don't need to handle. Oh, here I want to mention that this is you can easily encode the boundary conditions, no matter Neumann or direct boundary condition in the CN architecture. But if you use the PN, the physics to form neural network, which is a pointwise fully connected network, it's not easy to directly enforce the Neumann boundary condition. But for the direct boundary condition, you can introduce like some so-called specific solution and a distance function to impose that. I'm not sure if okay. So I saw the other questions. I can read it. So
two more questions.
Sure. How could you solve the stiffness of the PIN? Yeah, that's a good question. Since you have present the multi-scale demonstration for the Boson equation, how about the super resolution to the turbulence flow? Okay, this is a good question. So the stiffness of the PIN, like I said, there are several papers to discuss that. If you're familiar with the paper from Sifan from Paris group, they have discussed this from more like a theoretical perspective. But here, based on our experience, so the pointwise fully connected, definitely the stiffness is very high, and particularly like I said, if you put the boundary condition into the loss function, it's very hard to converge, and sometimes you need to manipulate the weight and make it converge fast. But if we do this discrete learning, the convergence is much easier. So like what I show in this case. So for example, like this case, you cannot get the simple result by using the fully connected pin. But here we use this, I didn't show the detail, we use the convolution LSTM structures and to solve this dynamic reaction diffusion equations. So we don't think, when we solve this, the stiffness is not a problem. It converges pretty fast. Sorry, where's my chat? Okay, here. So your second question is we are trying to this is like ongoing work. We are trying to super resolve the turbulence flows. It is definitely something we are interested, but I don't have a result to show you now, but I think it's doable. But definitely for the turbulent flow, it's more difficult. There are a lot of the intermediacy. It's super chaotic, so it's definitely more challenging problems, I would see.
Okay, we have time for another question, please.
Sure. So referring to page 33, let me go to.
Yeah, you can continue.
Yeah. So how is the comparison of the computational time between the PIM method and the fully CFD simulation for the Oh, you mean the computational time? So I think here, because that's really depend on like how to say it. So here we are using this learning not just to solve one equation at one boundary condition. Remember, we're trying to solve the parametric Navier-Stokes or parametric PDEs. So so basically, if you compare with the numerical simulation, when you change one boundary condition, you have to do one simulation, right? So it's really dependent on like how many input sample you want to propagate. So for example, in this 20-dimensional case, we basically train the network. I think we only use 20. I think we only use like 20 input samples. So the training cost for this one, I cannot exactly remember, but I need to check my paper. But several hours for this one, I think less than 3 hours if I check my paper. So, but if you but we propagate the sample for like 1,000 samples. So if you do the simulation, right? So you have to do it like 1,000 times. So, but I'm not sure if your question is if I just want to use the neural net to solve like one condition. That definitely for this case, the laminar flow, the CFD is much faster, especially for this 2D case. Give you some sense for this 3D case. So the CFD simulation for this one is three hours, but our training cost is less than like half hours. But we can, but when we do the inference, like after the training, the computation cost is trivial. So I'm not sure if I answered your question.
Okay, I think there are the last two questions, so I think then we can stop. So one question is if the Reynolds for the last few pages, I mean, you try this 737 is the highest Reynolds number that you tried, and what happened if you try with very high Reynolds number? That's
so so for this ongoing work, I'm with the highest Reynolds number is 1,000. So we didn't push it to the turbulence regime. I assume you are asking how it works for the turbulent flows, but we haven't move it to the turbulence case because I think the dynamics for the turbulence flows is going to be very challenged. So we didn't go to the turbulence regime.
Okay, and last question: how do you approximate the time derivatives with such method, as there is no history information and your PDEs are time dependent?
Yeah, that's a good question. I didn't show the details. So so for this case, we built like this auto-regressive. I don't have the slides, but we built this convolution LSTM. So the time dependence handled by the LSTM component, Rn component, and we also have the residual connection and auto-regressive formulation. So it's not like the purely CN for the dynamic problem.
Okay, good. So I think we can stop here. And yeah, we thank again Dr. Wang for this very nice talk. And yeah, I invite you to the next talk of our seminar series. And so thanks for everyone for attending, and thanks again, Dr. Wang.